Good morning, people. Big Bang Theory time. This is some seriously freaky science you're going to be doing today. I thought I'd do this as a recording rather than do it live, so this time you can play it back to yourself, you can rewind, you can slow-mo, whatever you want to do. And this is where we get into the detail of the Big Bang Theory. Now, I told you in the last lesson where the facts end and the theory begins, right? We have a lot of true observations that led us to think that the Big Bang Theory is the correct way that the universe began, and that the universe actually had a beginning. Now, we've fleshed this theory out to the nth degree, and today I'm going to tell you as many gory details as you need to know about the Big Bang Theory. So this is entirely theoretical. Everything I say, we have no real proof for, right? This might all be wrong, right? The entire thing. That's what theories are. They're based on observation, they're based on facts, they're backed up by a lot of evidence, but we can't prove it, and we genuinely don't know if it's right or wrong, or if it's true or false, if we're just full of ourselves. But this is our best guess. As far as the evidence is concerned, as far as everything we can see and detect about the universe is concerned, this is the most likely way that it began. Now, in books and online and so forth, if you Google Big Bang Theory, you'll get something like this quite often. Now, this is one diagram that's trying to explain to you what has happened to the universe since the Big Bang. This is where all of this detail comes that I'm going to give you today. I don't mind these things, but they just tell you a bunch of facts and they don't give you any explanation. So I'm going to explain this. I'm not even going to use this, but I'm going to explain the timeline of what happened to the stuff that came out of the Big Bang straight after the bang, right until today. Now, different textbooks and different online pages and different universities and so forth break this into a various number of stages. I've broken it into 4. This one's done 6. There's no real rhyme or reason, I don't think. So let's go. This is going to sound a little bit biblical. I apologize for that. In the beginning, there was only darkness. This is page 1 of Genesis, folks. So this is true. As far as we know, as far as the Big Bang Theory says, before 13.6 or 13.8 billion years ago, there was nothing around. There was no light, there was no stuff. There was only a thing that scientists have decided to call a primordial atom. Right? So the universe was microscopic. The entire thing, whatever the hell it was that was about to become the universe, was at that stage a tiny little thing, smaller than an atom, maybe even smaller than an electron. But it had either all of the energy or all of the matter that was going to become the universe. Now, we don't know how that works. We don't know why that happens. But again, this is our best guess. We could be wrong, we could be right. We'll never know. But it looks like that had to be the case. All right. And then, for reasons known only to itself, it exploded. About 13.6 to 13.8 billion years ago, this microscopic thing suddenly exploded, and it expanded at faster than the speed of light. Because there was so much pressure on the inside, when it went bang, it really went bang. It expanded, it got bigger and bigger and bigger at an incredible pace. It was probably the fastest expanding object of all time. And during that time, and this first stage only lasts for about 1 billionth or 1 million billionth of 1 second. So this is a very short first stage. The only thing that came out was photons, was light, and it wasn't light that you could see. Because there was an explosion of so much energy, all of the photons of light that came out would have been gamma rays. If you remember, it doesn't take much energy to make a long wave, but the shorter waves get, the more energy it takes to make them and the more energy they possess. So the shortest of all electromagnetic waves are the most energetic. And they would have been the ones that were coming out of this primordial atom right in the very first sort of finger snap of the universe. There was no matter yet. It was just energy in the form of photons. Now, after a very small amount of time, after about, like I said, about 1 million billionth of a second, the second phase happened. Matter turned up. Now, the obvious question is, how the hell does matter turn up out of light? Well, this is where Einstein comes in. The Big Bang Theory wasn't possible until Einstein came up with the most famous piece of science of all time, this one, E equals mc squared. This is the one scientific formula that everyone's heard of. People who know nothing about science have heard of E equals mc squared. They just don't know what the hell it is. Well, I'm going to tell you. This is what it is. Energy and matter can actually change between each other. You can destroy energy, and that doesn't mean change it into another form. Though when you use a toaster, you don't destroy electricity. You change that electrical energy into heat and light and maybe a little sound if the toaster buzzes. But the energy can still be accounted for. It's still, we still know where it went. It still exists. It just exists in another form. But you can actually destroy energy, so the universe has a bit less energy. And when you do that, you create matter. And you don't create much matter. It takes an enormous amount of energy to create a tiny, tiny bit of matter. Right? So this is what Einstein came up with. This is one of his more famous bits. It's probably the most famous bit that he came up with. So c is 3 by 10 to the 8. It's the speed of light. Right? And if you square that, you get an enormous number, 9 by 10 to the 16. So what this means, if you read this, is that if you could destroy 9 by 10 to the 16 joules of energy, you will create 1 kilogram of matter, of atoms and protons and neutrons and stuff like that. So it takes a massive amount of energy. To put that in context, 9 by 10 to the 16 joules, that's about as much electricity as Melbourne uses in 4 months. That's a massive amount of energy to make 1 kilogram of matter. And this works the other way around as well, by the way. You can actually destroy matter and make energy. Right? And obviously, because of the way this formula is, if you destroy a small amount of matter, you create an enormous amount of energy. Right? This is how nuclear power plants work. We destroy a very, very tiny amount of matter and we make lots of energy, and we turn that energy into electricity. It's also how atomic bombs work. We destroy, when Hiroshima was flattened, we destroyed about 1.5 kilograms of uranium. Right? Planet Earth lost weight that day. It lost 1.5 kilograms of weight. That matter didn't turn into something else. It simply ceased to exist, and out came about 1.5 times that many joules of energy right over the top of Hiroshima, and there went the town. All right, so the second phase of the Big Bang is the creation of matter. All of that energy, all of those gamma photons that were there, started banging into each other and started turning into matter. A lot of them destroyed themselves and turned themselves into matter. Now there's another part of this that you may have heard of that will need some explanation. You may have heard of antimatter. It does exist. It's not something that's just written in sort of science cartoons and movies and things. Antimatter does exist. Let me explain a few things here. It turns out there are 2 types of matter, and we've called the other one antimatter. It's just another type of matter, but they're opposites of each other. They have the same qualities. For example, a matter proton is identical. It's not almost. It is identical to an antiproton, but a matter proton is positively charged and an antiproton is negatively charged. It's a negatively charged proton. Apart from that, they're clones. So antimatter is essentially clones of each other. So there's an antimatter version of every sort of matter that you've heard of, right? There's an anti-hydrogen atom, there's an anti-oxygen atom, there are anti-water molecules. Right? There is such a thing. There might even be anti-U somewhere. That's a concept, isn't it? But when all of that energy destroyed itself early in the Big Bang and started turning into matter, some of it turned into matter and some of it turned into antimatter. Now, 2 things you need to know. Firstly, they're clones of each other apart from their charge, apart from one little difference. And the other thing you need to know is if that and that touch each other, they annihilate. If a piece of matter, a fundamental piece of matter, one of these little basic building blocks that we know of, touches its antimatter equivalent, they annihilate. If it touches one of those things that's not its equivalent, they just bounce off each other. But if the 2 opposites attract and attach to each other, they cease to exist, and that matter destroys itself and energy comes out in the form of those gamma photons. So we basically go backwards. Now, when we got to this stage 2 matter creation part of the Big Bang Theory, right, and this lasted for quite a while, this lasted for a few years, there was a whole lot of matter being made and a whole lot of antimatter being made, and because everything was so hot and so very quickly moving and so very violently colliding, a lot of this just annihilated itself straight away. It came into existence, hit each other, and destroyed itself. So there was a lot of matter being created, destroyed. It was all very chaotic because this was all happening at a couple of billion degrees. So for a while there, the universe did get heavier, but there was a lot of destruction in amongst this enormous amount of creation. And it turned out, we don't know why, but it turned out that the amount of matter that was made was a little tiny bit more than the amount of antimatter that was made. And so when matter and antimatter collided and annihilated themselves, once all of this was gone, there was a little bit of that left over. And by a little bit, I mean everything we've got in the universe now. So what's left of the universe, all the stars and the galaxies and planet Earth and us, that's the little tiny bit of matter that was left over when all of the antimatter was suddenly exhausted. And consequently, there's very little antimatter left in the universe. It's just some bits and pieces of it floating around in space, unable to find one of these things to touch and destroy itself. There is some around, and we can actually make it. It does genuinely exist. This is not a concept. This is one of the facts in this otherwise theory. Antimatter does exist. So at the end of the second phase of the universe's creation, we ended up having a whole pile of matter, having had a whole pile of this as well, but it had all destroyed itself. And it was also starting to cool down, and that had an effect. The very first types of matter, there you go, the very first types of matter that were created out of those photons, right, when the temperature was 1 billion degrees and everything was going fast, and when E equals mc squared first happened and we got the first M, the first matter, it was fundamental particles. It was the little bits and pieces that make protons and neutrons and electrons. It wasn't even protons, neutrons, and electrons. It was things called quarks, right? Q-U-A-R-K-S, quarks. Right? Now, it was so hot that even though these guys are attracted to each other and they tend to stick together to make protons and neutrons and electrons, they couldn't because they were moving so quickly because the temperature was a couple of billion degrees. So at the moment, matter couldn't organize itself. It was just all these bits. It was like Lego blocks in a cyclone. They can hit each other, but they can't click. As the temperature cooled down, these guys finally got close enough to each other and moving slow enough so they could actually stick when they joined together. Now, the force that sticks them together is a very strong force called the strong force. Stayed up all night to figure out that name. That's genuinely true. There's a thing called the strong force that holds protons together and holds neutrons together and holds electrons together. They are themselves made of some parts called quarks. We'll worry about the details of that later on. Right? But at this stage, the temperature was still millions of degrees, and these guys couldn't get together to make atoms. They were moving too fast. Protons and neutrons would hit each other and bounce off instead of sticking together to make a nucleus. And there was no way that an electron was going slow enough to actually stop and orbit around a positively charged nucleus, even if a nucleus was there. But eventually it did cool down, and the very first atoms were made. Right? These things started getting slow enough so that they could bump together and stick together under the attraction of the strong force. And finally, electrons stopped going so fast that they just whisked past these things and started getting captured in those orbitals and started orbiting and stayed there and reached a point of stability. And the very first atoms were born. So at the end of this second phase, at the end of the phase where matter was created, we've got all of the matter in the universe, but all it is one big featureless cloud of atoms. And the atoms were almost entirely hydrogen atoms because you didn't get big nuclei at that stage. This is like bigger than anything that would have been in that primordial sort of cloud. So it was predominantly hydrogen, maybe a little bit of helium, maybe a tiny bit of lithium, but it was really small atoms, and it was featureless and it was dark. There was no light left. It had all turned into matter. Now part 3, phase 3, was one that video that I got you to watch with Sam Neill did fairly well. This was when they played the classical music and showed you the swirly cloud, and it ended with the first stars being created. this featureless cloud of stuff, luckily for us, had some ripples in it. If it was beautifully evenly spread, if there was no difference in the density of the cloud over here and the density of the cloud over there, then nothing would happen, and the universe would still be a big featureless, non-moving cloud of hydrogen. But luckily, there were some bits that were a little bit denser than others, and this is where gravity starts taking over. This is when we say, thank God for gravity, because gravity changed the world, changed the universe. Right? If there's a dense cloud of stuff over here, then it weighs a little more for its size than a non-dense cloud of stuff over here. And it attracts things to it. Right? Now, if there was no density difference, then every little bit of the cloud would be equally attracted in all other directions, and none of them would have moved. They would have all stayed apart from each other. An atom there, an atom there, an atom there, an atom there would have stayed exactly still, non-moving forever. Luckily, there were some areas that were denser than others, and that sort of got the cloud moving and swirling and in some places coagulating together, and atoms became molecules because it was still pretty hot. There was still a lot of vibrational movement around. There was still a fair bit of energy in it. There just wasn't any light anymore. This was completely pitch black for about 370,000 years, we think. This is sort of the dark ages of the universe. About 370,000 years of this big featureless hydrogen cloud slowly collapsing in on itself. You know how weak gravity is. People think that gravity is a strong force, but it's an incredibly weak force. It takes a whole planet for you to even feel it, and you can still beat Earth's gravity. You can jump, right? So your little scrawny leg muscles can beat the gravity of all of planet Earth. A fridge magnet can beat all of the gravity of Earth and hold something against the fridge. Right? The whole planet's gravity is trying to pull that magnet off the fridge, and it doesn't do it. Gravity is weak. Right? So you can imagine how weak the gravity between one atom and another atom is. Not a lot of attraction there. They're not really falling towards each other like lovers in a movie. Right? It doesn't quite work that way. So it took 370,000 years. This is our best guess again. It's all a theory. It took about that much time for this cloud to become anything other than just a bunch of droplets of atoms. But eventually, those denser parts got more and more and more matter inside them. And because they were getting heavier, their own gravity was getting stronger and stronger and stronger. And the bigger these clouds got, the faster they could attract more things. So it became a self-fulfilling prophecy. It became an accelerating process. And eventually these things got so heavy in the middle that there was so much pressure in the middle that the atoms in the very middle, once there was like kilometers and kilometers, bigger than Earth-sized cloud of gas, right? Bigger than the sun-sized cloud of gas around this dense center. In the center, under all that gravity, all that attraction, atoms were being forced together. Nuclei were being squeezed together. A hydrogen nucleus and a hydrogen nucleus were squeezed together to make a helium nucleus, and that releases a lot of energy because the mass of a helium nucleus is a little bit less than the mass of those two hydrogen nuclei. Right? And E equals mc squared comes into play again. We destroyed a little bit of mass, we get a lot of energy. And that is the fuel. It's called fusion. That's the fuel that runs every star. And when that process began to happen, that's when the dense cloud of gas that had been turning into a ball became a star. Right? And finally, the universe wasn't dark anymore. It seems that the first stars turned up about 200,000 years after the beginning of the Big Bang, right? About halfway through this 370,000 years. But one little star in a big universe still keeps the universe pretty dark. It wasn't until about 370,000 years after the beginning, after the Big Bang itself, that there were enough stars to really call the universe lit up. Now, since then, all that has been happening is the stars and the galaxies that had been created and the nebula and all that sort of stuff and the planets going around the stars, all of that was formed at the end of that 370,000 years. The only thing that has been different is that it has been expanding. It's been doing that sort of that balloon trick that I told you about the other day. Right? And that's where we get to the current point where we can now look up at the sky and see that it is still expanding. So, in summary, these are my 4 phases of the Big Bang Theory. Right? Most books put it into 3 or 4 or 5 or 6 different phases, but I reckon there's 4 distinct things. The very beginning, the very short beginning, it was bright. Right? It was only making light. It was unbelievably hot, hotter than you can imagine, billions of degrees. It was making gamma photons by the truckload, and there was an explosive rate of expansion. It got bigger very, very quickly. And then it started making matter, and it got heavy. This is the second phase. The second phase took quite a while. Excuse me. It was still hot, but it was cooling down, and matter was created using E equals mc squared. Lots of energy was used to make not much matter. So given that not much matter is actually all the galaxies of the universe, you can imagine how much energy there must have been. Right? And matter and antimatter were being made, and when they hit each other, they started destroying each other, and there was a little bit of matter left over at the end. Thank the Lord for that, because that's what we're made of. And then it got cool enough so that the photons that were still going around were not light. They were not visible to the naked eye. They were there. There was light energy going around, but it wasn't in those wavelengths of red, orange, yellow, green, blue, indigo, violet. So everything was dark. Right? It was still hot, but it was cooling down. It was just a featureless cloud of gas, predominantly hydrogen. There was no light at all until the first stars. This is the dark ages of the universe. Right? And this was all running by gravity. Right? Gravity did all of the work, did all of the heavy lifting, literally, to turn the universe into what it is today. At the end of the dark ages, the universe pretty much was what it is today. The stars were there, they were swirling around in galaxies, galaxies were making clusters of galaxies, etc. There were planets being formed, going around stars. It was all in place. It was just a lot closer and a lot more tightly packed than it is now. If you'd looked up, if we could have been there on a planet at that time and looked up in the sky, there would have been way more stars and way less black because everything would have been closer. Since then, and this is only about 1 billion years after the beginning, so this is all happening in 1 billion years. For the next 12.6-ish billion years, this has been happening. It's just been cooling down, transparent, lit up, and going away from each other. So that, my friends, is the Big Bang in detail, in plain English. The best thing you can do right now, having heard all of this, is go and read the relevant section of your book. Check out the email. I think it was section 5.2, but whichever number it is, read the relevant section on your book about the Big Bang, and what the book says will make a lot more sense having seen this. See you later.